Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 8, Projectivities in One-Dimensional Forms. Section 78, Involutions. An involution was defined, page 102, as any projectivity in a one-dimensional form which is of period 2, i.e., by the relation iota squared equals the identity, where iota is not equal to the identity, where iota represents an involution. This relation is clearly equivalent to the other, iota equals iota inverse, where iota is not equal the identity, so that any projectivity, not the identity, in a one-dimensional form which is identical with its inverse is an involution. It will be recalled that since any involution makes every pair of homologous elements correspond doubly, i.e., A to A prime and A prime to A, an involution may also be considered as a pairing of elements of a one-dimensional form. Any such pair is then called a conjugate pair of the involution. We shall propose now to consider this important class of projectivities more in detail. To this end, it seems desirable to collect the fundamental properties of involutions, which have been obtained in previous chapters. They are as follows. 1. If the relation pi squared of A is equal to A holds for a single element A, not a double element of pi, of a one-dimensional form, the projectivity pi is an involution, and the relation holds for every element of the form. Theorem 26, Chapter 4. 2. An involution is uniquely determined when two pairs of conjugate elements are given. Theorem 26, Corollary, Chapter 4. 3. The opposite pairs of any quadrangular set are three pairs of an involution. Theorem 27, Chapter 4. 4. If M and N are distinct double elements of any projectivity in a one-dimensional form, and A prime, and B prime are any two pairs of homologous elements of the projectivity, the pairs of elements Mn, AB prime, A prime B are three pairs of an involution. Theorem 27, Corollary 3, Chapter 4. 5. If Mn are double elements of an involution, they are distinct, and every conjugate pair of the involution is harmonic with Mn. Theorem 27, Corollary 1, Chapter 4. 6. An involution is uniquely determined if two double elements are given, or if one double element and another conjugate pair are given. This follows directly from the preceding. 7. An involution is represented analytically by a bilinear form, Cx prime minus A times the quantity x plus x prime minus B equals 0, or by the transformation x prime equal the quantity ax plus b divided by the quantity cx minus a squared plus bc not equal to 0. Theorem 12, Corollary 3, Chapter 6. 8. An involution with double elements m, n may be represented by the transformation, the quantity x prime minus m divided by the quantity x prime minus n equals negative the quantity x minus m divided by the quantity x minus n. Theorem 1, Corollaries 2 and 3, Chapter 8. We recall finally the second theorem of Desargues and its various modifications, section 46, Chapter 5, which need not be repeated at this place. It has been seen in the preceding sections that any projectivity in a one-dimensional primitive form may be transformed into a projectivity on a conic. We shall find that the construction of an involution on a conic is especially simple and may be used to advantage in deriving further properties of involutions. Under duality, we may confine our considerations to the case of an involution of points on a conic. Theorem 16. The lines joining the conjugate points of an involution on a conic all pass through the center of the involution. Proof that A prime, figure 90, be any conjugate pair, A not a double point, of an involution of points on a conic C squared. The line A prime is then an invariant line of the collineation generating the involution. Every line joining a pair of distinct conjugate points of the involution is therefore invariant, and the generating collineation must be a perspective collineation. Since any collineation leaving four lines invariant is either perspective or the identity. Theorem 9, Corollary 3, Chapter 3. It remains only to show that the center of this perspective collineation is the center of the involution. Let B, B prime, be not a double point, be any other conjugate pair of the involution distinct from A prime. Then the lines AB prime and A prime B intersect on the axis of the involution. But since B, B prime correspond to each other doubly, it follows that the lines AB and A prime B prime also intersect on the axis. This axis then joins two of the diagonal points of the quadrangle A prime, B prime. The center of the perspective collineation is determined as the intersection of the lines A prime and B prime, i.e. it is the third diagonal point of the quadrangle A prime, B prime. The center of the collineation is therefore the pole of the axis of the involution, Theorems 14, Chapter 5, and is therefore, Theorem 14 above, the center of the involution. Since this center of the involution is clearly not on the conic, the generating collineation of any involution of the conic is a homology, whose center O and axis O are pole and polar with respect to the conic. A homology of period 2 is sometimes called a harmonic homology, since it transforms any point P of the plane into its harmonic conjugate with respect to O, and the point in which OP meets the axis. It is called a projective reflection or point-line reflection. Clearly, this is the only kind of homology that can leave a conic invariant. The construction of the pairs of an involution on a conic is now very simple. If two conjugate pairs A prime and B prime are given, the lines A prime and B prime determine the center of the involution. The conjugate of any other point C on the conic is then determined as the intersection with the conic of the line joining C to the center. If the involution has double points, the tangents at these points pass through the center of the involution. And conversely, if tangents can be drawn to the conic from the center of the involution, the points of contact of these tangents are double points of the involution. The great importance of involutions is in part due to the following theorem. Theorem 17. Any projectivity in a one-dimensional form may be obtained as the product of two involutions. Proof: let pi be the projectivity in question, and let A be any point of the one-dimensional form, which is not a double point. Further, let pi of A equal A prime, and pi of A prime equal A double prime. Then, if iota 1 is the involution of which A prime is a double point, and of which A double prime is a conjugate pair, proposition 6, page 222, we have iota sub 1 dot pi of A prime equals A prime A. So that in the projectivity iota sub 1 dot pi, the pair A prime corresponds to itself doubly. Iota sub 1 dot pi is therefore an involution. Proposition 1, page 221. If it be denoted by iota sub 2, we have iota sub 1 dot pi equals iota sub 2, or pi equal iota 1 dot iota 2, which was to be proved. This proof gives at once Corollary 1. Any projectivity pi may be represented as the product of two involutions. Pi equal iota sub 1 dot iota sub 2, either of which, but not both, has an arbitrary point, not a double point of pi, for a double point. Proof: we have seen above that the involution iota sub 1 may have an arbitrary point, A prime, for a double point. If in the above argument we let iota sub 2 be the involution of which A prime is a double point and A double prime is a conjugate pair, we have pi dot iota sub 2 of A prime A double prime equal to A double prime A prime. whence pi dot iota sub 2 is an involution, say iota sub 1. We then have pi equal iota sub 1 dot iota sub 2, in which iota sub 2 has the arbitrary point a prime for a double point. The argument given above for the proof of the theorem applies without change when a is equal to a double prime, i.e. when the projectivity pi is an involution. This leads readily to the following important theorem. Corollary 2. If a prime is a conjugate pair of an involution iota, the involution of which a prime are double points transforms iota into itself, and the two involutions are commutative. Proof. The proof of Theorem 17 gives at once iota equal to iota sub 1 dot iota sub 2, where iota sub 1 is determined as the involution of which a double prime are double points. We have then iota sub 1 dot iota equals iota sub 2, from which follows, by taking the inverse of both sides of the equality, iota dot iota sub 1 equal iota sub 2 inverse equals iota sub 2, or iota sub 1 dot iota equal iota dot iota sub 1, or iota sub 1 dot iota sub 1 equal iota. As an immediate corollary of the preceding, we have Corollary 3. The product of two involutions with double points a prime and b prime respectively transforms into itself the involution in which a prime and b prime are two conjugate pairs. Involutions related as are the two in Corollary 2 above are worthy of special attention. Definition. Two involutions are said to be harmonic if their product is an involution. Theorem 18. Two harmonic involutions are commutative. Proof. If iota sub 1, iota sub 2 are harmonic, we have by definition iota sub 1 dot iota sub 2 equals iota sub 3, where iota sub 3 is an involution. This gives at once the relations iota sub 1 dot iota sub 2 dot iota sub 3 equal the identity, and iota sub 1 dot iota sub 2 equal iota sub 2 dot iota sub 1. Corollary. Conversely, if two distinct involutions are commutative, they are harmonic. For from the relation iota sub 1 dot iota sub 2 equals iota sub 2 dot iota sub 1 follows the quantity iota sub 1 dot iota sub 2 squared equals the identity, i.e. iota sub 1 dot iota sub 2 is an involution, since iota sub 1 dot iota sub 2 is not equal to the identity. Definition. The set of involutions harmonic with a given involution is called a pencil of involutions. It follows then from Theorem 17, Corollary 2, that the set of all involutions in which two given elements form a conjugate pair is a pencil. Thus, the double points of the involution of such a pencil are the pairs of an involution.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.